So there's really, there's one last thing that's sort of going to tie this all together. And if we just sort of quickly summarize what we've looked at ARPs, traditional decline curves. We've looked at the type curve methods, and we saw there were 2 or 3 different type curve methods that were useful. There's others that are out there. We've just sort of focused on what we feel are the most effective ones. We looked at the flowing material balance method. And we looked at some new methods specialized in Wattenberger type curves that have just become much more valuable in recent years because of the types of reservoirs that are being drilled these days. The final part that's going to kind of tie this all together is modeling and history matching. After we've done our interpretation using these various techniques, what we want to be able to do is come up with a model that's going to allow us to validate our interpretation. And let me talk a little bit about what this means. Basically, what a model is going to allow us to do is it's going to allow us to put some result or input parameters in and generate either simulated production volumes or simulated production rates. And then the idea is we history match those to our real data to see whether or not we've got a good fit. So before I move forward with that, I want to show a little bit of a picture of what this looks like. And the idea is we want to get an understanding as to why we would be interested in doing a model history match. You know, why isn't it just good enough to do an interpretation of the data? And I have what I call my little circle of life here, and the circle, or at least the circle of production data analysis. And what it looks like is it looks a little bit like this. Okay, we always start with data. That's the first thing that we see as production engineers and reservoir engineers that are analyzing, and or production analysts. The first thing that we're going to see is the data. So the first thing that we're going to do is we're going to do analysis and interpretation. And analysis and interpretation are your ARPs, your type curves, your flowing material balance, and any other methods that you have out there. And basically what all these things have in common is they take data in and they generate results out. Okay? So they're going to give me results. If I follow the circle around, they're going to give me results in the form of permeability, skin, XF, original gas in place, drainage area, you name it. Okay? All the results that I can get, and I'm pulling those results out of the data. This is actually, interestingly enough though, this is actually the reverse of modeling. This is what we call inverse or reverse modeling, because we started with the data and we're trying to extract what it was that went into that model. The forward modeling process actually takes the results, so this is going to be modeling or history matching. And brings you back to the data again. So this is why I kind of call it the circle. If you can get from here to here, well, you've done okay. You've got some numbers out of it. But if you can bring it back and reproduce the data that you started with, your level of confidence goes from here to here. Okay, you've closed the gap. Everything is now internally consistent. So there's a huge amount of value to going and closing that loop with doing the modeling. Okay, and now you've done a complete analysis. So reverse modeling goes this way. Forward modeling brings it back to the data. We do a history match. We try and match the data. That validates our interpretation. The types of models that we can use to make this happen are have as much variety in them as you want. You can go to the level of full simulation and include non-Darcy flow effects, wellbore storage, heterogeneities, multi-layers. I mean, you can go as complex as you want with these things. Usually there isn't a huge amount of value with adding arbitrary complexity unless you have corroborating data, input data that's going to there's going to be a reason for doing that. So we typically, when we do production data analysis, start with very simple models and add complexities as we need to. Okay, so we can build on the model if we feel the need to do it or we have a reason for doing it, or we can just keep the model simple and go from there. So we can use vertical well models, fracture models. There's other things that aren't shown here, such as composite multi-layer models. This is a horizontal well model. So there's lots of different options out there. Analytical models and numerical models. Okay, so before we get to the next subject there, we'll just very quickly go and show an example of modeling. And I'm going to go back to my boundary-dominated flow example. Okay, so here's my model. I'm going to seed the model. And seeding the model is really just putting some input parameters in. That's this part. Okay, so I've made some estimates of what permeability, XF, original gas in place are. And I'm going to populate the model with those numbers and try to reproduce the data. If I haven't done this part first, then I've got nothing to populate the model with. So the analysis interpretation part is obviously very important. That's where I get the input parameters for the model. So I've done this, and now the bottom plot on the left-hand side is going to show me my history match. And you can see a little bit of it right here. This is a pressure history match, and it's dropped right off into negative territory. I'm nowhere near matching the dotted lines, and I'm not sure why that is. Let me go back and see. Okay, well, I'll pick a different curve here. Let's go to radial, and let's say that's going to be my match. So I'm happy with that match. I'm going to go back to my analytical model, and I'm going to repopulate that model with that data. So by clicking on that button, I've basically said, put all those numbers from that Blasingame result into the model and generate me a history match. So that's what it's done. So now let's look at the history match. Well, we've got a solid line here which indicates the simulated flowing pressure in the system, and then we've got the brown dots which indicate the actual measured pressures in the system. And so what I'm going to do now is, it's pretty good. It's a fairly good quality match, but I could make it a little bit better. So I'm going to use my automatic parameter estimation to improve the match. And these are just software tools that we have available. And we can go from there. Now, typically what you want to do in this sort of situation is make fine-tune adjustments, because we don't want to really change our interpretation. We want to make sure that the numbers are close, but by fine-tuning it, we can get, okay, this is mathematically the best possible fit of this data. We're not doing an entirely new interpretation. We know basically what the numbers are. We're just fine-tune adjusting them so that it gives you the best fit of that data. Okay, so modeling will let us do that. It'll validate the interpretation, allow us to fine-tune it to get the best possible match, and then we have one final answer. Instead of having 8 different interpretations, you've got one final answer with the model, and then we're in good shape.